Okay, let's quickly walk through an implementation of the multi-class logistic regression, basically the so-called Softmax regression or this approach 2. Okay, the usual stuff, loading MNIST. Now we are going to use about 6,000 data points to actually train the logistic regression, I guess. We have 9 categories, 0 to 9, and then we are going to convert train Y, the output for the training set, which is one of these 9 numbers, into this one hard-coded version of the 9 numbers. Okay, so if we run these things one at a time, so train Y is just numbers between 0 and 9, and then train Y one hard-coded, where is that? Here is it, this quantity. So each row corresponds to a single output, and this one corresponds to the number 9 because there's a 1 in the 10th place, and this one will be, so this corresponds to 0, 1, 2, 3, 4, 5, 6. So this is probably output number 6, and so on. So 9, 6, 8, and so on. Okay, so that's how you do one hard coding. You put a 1 in the place of the class that that particular output belongs to. Okay, once we've converted into that format, everything else is the same as before. Your X matrix definition, B input. Now previously, when we were doing binary classification, B input was just this vector size plus 1 comma 1, where you just had one of 2 categories, right? So now we've defined B input as a matrix with 875 rows and 10 columns. Num categories is 10. We have 10 columns. So we have 785, I guess, not 875, times 10 unknowns in B input. Okay. So let me run these things. So here we are just defining the initial seed, the options for the optimization, and then we just optimize. Now again, this logistic class function exactly the same as before, except now the function is slightly different. If you look at the old functions, you first find Z, which is basically your X matrix times B, which is taking each input and going B naught plus B1 input 1 plus B2 input 2, and so on. So we do that, and then we apply what's called the Softmax function, which is kind of a misnomer, which I might address in a different video. But basically, at least in this part of machine learning, this function which is basically the logistic function, when applied to the multinomial case or multiclass case, basically this function is called the Softmax function. Okay, so if you give it a list of zi's, z1, z2, z3, what it will output is the Softmax function, what the Softmax function outputs. So I've written the Softmax function here. It's somewhat cryptic sounding. You can look at the comments here. But essentially what it does is evaluates this expression. It computes e power zi for each I, and then adds them all up, puts them in the denominator. The numerator is e power z1, e power z2, and so on. So given z1, z2, z3, you get e power z1 divided by sum of e power zi, e power z2 divided by sum of e power z2, and so on. So that's actually what you get. And what is that meant to be? That's actually meant to be the prediction for the probability for each class, right? So qi is basically your best attempt at predicting what the probability that the given image belongs to class I. So I'm calling that Y because that's the output. And then we have this Y data, one hard coded, which is what we saw before. or y list. What was it? Train y, one hard coded, if you recall. Okay. This thing. And then we are finding what's called a cross entropy with respect to y model, right? So y model is predicting these probabilities for each image, and this is the probability that this image belongs to class 9, class 8, class 7, and so on. So we find this thing called a cross entropy, which is the same as the logistic log loss function for multiclass, and it basically multiplies your y and y data and y model with the log on the y model, and then sums it, and then takes the mean of all that, right? So it's basically this function is being evaluated. Okay. And then once you evaluate it, we can just optimize it, run it. The optimization is rather slow, so I've run it and it's taking some time. Let me wait until perhaps it does one iteration. It's taking longer than usual. It's possible that because I'm recording this video, this is taking much longer. Okay, there you go, one iteration. My guess is if I'm not making this video, it'll run a bit faster. Let me just Control C out. If you let it run for a while, it will eventually converge or do something. At least it'll get to a pretty good answer. And I've stored the answer here in this data file called .class all digit 6000 image. So let me just run it from there as if I have run the optimization calculation. So if we actually do the test accuracy for this logistic regression, it's about 87%. So now the accuracy corresponds to not just binary classification, it basically makes a prediction for each image in the test data set, and we are comparing the accuracy. There is this next cell. We can also compute, of course, the false positive, false negative, but now we'll have to do that for each and every number, right? The notion of false positive and false negative relies on you defining what a positive is. So you will have to sort of define it for each and every number. Okay, so sort of doing that, one way of doing that is, or representing that, is this thing called a confusion matrix, which compares the true class and the predicted class for this particular classifier. Okay, so when the true class is 9, the predicted class is sometimes 0, sometimes 1, sometimes 2, sometimes 3. In other words, 5. On 5 occasions, when the true class is 9, the predicted class is 5, and so on and so forth. On some occasions, when the true class is 9, the predicted class is 4. There's quite a high number of 4s when the true class is 9, presumably because 4 sometimes looks like a 9, right? 7 also looks like a 9. So when the predicted class is, when the true class is 9, an unusually large number is labeled as 7. A pretty small number is labeled as 6, which is interesting. But most of the time, so 846 times, the when the true class is 9, the predicted class is also 9, right? So notice that when the true class is 0, most of the time the predicted class is 0. When the true class is 1, most of the time the predicted class is 1. But occasionally the predicted class is 8, whatever, right? So this actually tells you, this incorporates, these numbers actually incorporate false positives, false negatives, and all that. Sort of tells you in a very sort of comprehensive manner how good the classifier is in classifying a particular number or a particular kind of an image. So, right, so it gives you a complete picture in some sense. So that's very nice. This is called a confusion matrix. Confusion matrix, and MATLAB has this command for it, which just uses the actual data and then the actual predicted categories, and it compares all those things to make this chart. Okay. And then our usual thing of actually displaying an image and seeing what our classifier does. We already saw that it's got a 86% accuracy or 87% accuracy. Let's see what that looks like. Okay, we also denote the probability that it feels sort of a confidence number, a quantification of confidence in its output. So the MNIST thinks it's 2, our classifier thinks it's 2 with probability 1, basically, very high confidence. So it's getting things right, and when it gets things right, its confidence is very high. Let's see if it makes an error. So far so good. No errors so far, or at least none that I saw. Okay, so for some reason it's 6 and it thinks it's a 0, but with 99% probability. So it's got a very high confidence even though it's actually wrong. So that's interesting. Okay, so I suppose I just ran 20 images and I put a pause of about 5 seconds in between just so that we could see things. Anyway, so that's the multi-class multinomial logistic regression, or sometimes called the Softmax regression, because of the use of this function. Like I said, because of the use of this function, which is called the Softmax function, or sometimes called the Softmax function. Okay, maybe I just want to briefly go over how the probabilities were computed. Once you have an image, you essentially multiply the image vector with an extra 1 with b result, and you get a z value, and then you can convert the z value for each class into probabilities by applying the softmax, basically this function. It goes from 0 to probabilities, and then we pick whichever probability is the highest. That's going to be the highest probability, and then the index of the probability is the class that it belongs to, I guess, or the index of the class that it belongs to. And then I just say MNIST thinks it's whatever, our classifier thinks it's categories of index max with probability prob max, which is this maximum probability. So that was what was the output of that last figure. Okay, I guess in the next homework we will try to apply this method to maybe other data sets not containing numbers and see if it works at all.